I will use an example circuit to discuss about mesh current analysis or loop current analysis. For this circuit, we need to find out the currents through each of the branches. So in order to do that, what we do is we assign loop currents or mesh currents for each of the loop or mesh present. So here we can see there are two loops present, this one and this one. So we assign a current. Let's assign two currents for each one current. So this is a fictitious current. This is not the practical, because of course the current will be different in this branch and this branch, but we assign a loop current here, and we are assigning a counterclockwise one, another one here. So I1 and I2, and once we have assigned the currents, we write the KVL equations for each of the loops. So loop 1, which is this one, the drops, so we have to write the drops like this one, for this one plus minus, because the current is in that direction, in the counterclockwise direction. So 45 is a rise going in the counterclockwise direction, and then 2I1 plus 12I1 minus I2, and then 4I1. So 45, and then we have 18I1, 18I1, and then minus 12I2. So this is one equation, and then we write the loop KVL equation for the second loop. So this is for loop 1, and this is for loop 2 or mesh 2, whatever. So this one is again, now the drops will be in a different direction. So since the current is counterclockwise in this loop, the drops are like that. So yeah, so what I do, if I go in the counterclockwise direction, I can see the 30 volt is also a drop. So if I write on the other hand, on the left hand side in this case, so that will be a negative sign, and then 9I2 plus 3I2 plus 12I2 minus I1, so that's minus 30, and then 9 plus 3 plus 12, which is 24I2. So 24I2 minus, that is 12I1, or I can write it like that, minus 12I1 plus 24I2. So this is equation 2. Now in order to solve this one, these are two linear equations, two simultaneous linear equations, and we can adopt what is known as Cramer's rule. It's a matrix, just writing the matrix for the equations. So this is the same thing as it was done for the mesh current analysis, node voltage analysis, and this is actually the determinant method. So let me write in, I didn't write in matrix form, so let me write that in matrix form. So what I will do, I will write the right hand first. So 18 in the matrix, so 18 and minus 12, and then 12 here, minus 12 here, and then this one is 24 here, and then I1, I2, I1 and I2, and then on the right hand side I have 45 and minus 30, 45 and minus 30. So this is the matrix form of the equation. Now in order to solve this, we need to write the equivalent determinants. So basically, if the determinant of this is delta, so that would be delta 18 and then minus 12 and 24, and then delta 1 for the first one will be 18 minus 12 and then 45 minus 30, and delta 2 will be 45 minus 30 and minus 12, 24, like that. So these three, so here it will be 18 times 24 minus 12 times 12, so that one is 288, and then we have 18 times minus 30, and then minus, that becomes plus 45 times 12. So this is becoming minus 540 plus 540, and this is 0 here. And then finally there is one mistake. This one is actually delta 2 because I have written the 45 and 30 on the second row of the second column of the determinant, so it is actually delta 2, and this one is delta 1 because I have written the right hand side, or maybe rather the left hand side here on the first column. So this one is actually delta 1, but anyway, so 45 times 24 minus 12 times 30, so that's actually 720. So now we can see I1 will be delta 1 over delta, and I2 will be delta 2 over delta. So basically this one is delta 1 because our I1 is this one, and then yeah, just looking at this form we know why I1 is like that, because this one is written in this column for I1, and for I2 this one will be written in this column in the determinant, of course. So anyway, this one becomes 720 over 288, and that one is 2.5 amps, while this one is 0 anyway, so basically the current is 0. So we have both the currents, and we have applied Cramer's rule determinant method for solving the linear equations.